Now we switch to voltage. So we've looked at resistance, how to handle the resistors in series. We've looked at how to handle the current and the current in series. Now let's look at how voltage differs. Remember, current goes through, voltage is across. So if we look at first the sources, since all the voltage comes from a source, it makes sense that we look at sources first. So when two or more voltage sources are in series, the total voltage is equal to the algebraic sum of the individual source voltages. So if we look down here at the bottom at the diagrams, 1.5 volts, 1.5 volts, 1.5 volts, the algebraic sum of those is 4.5 volts. Okay? If we look at the B section over here, 1.5, 1.5, 1.5. Okay, notice that polarity matters. We've got one of those 1.5s reversed. So it's 1.5 minus 1.5 plus 1.5. So we have a total of 3 minus 1.5, which gives us 1.5. Over here we see 9 volts, 9 volts, 9 volts, gives us a total of 27 volts. So the algebraic sum means that the polarities of the sources must be included when the sources are combined in series. Sources with opposite polarities have voltages with opposite signs. So generically speaking, our relationship says that the source total is equal to each of the individual sources, 1, 2, 3, 4, 5, out to n, and we have to observe the signs. So if we look here from the first example, again, all of them are positive, we end up with 4.5. B, we have one of them that's reversed, negative, we end up with 1.5. So 4.5 total of all three of those, 1.5 the three of those. So polarity is important. Always be sure that you account for polarity when you are adding the sources. So if we look at this example, what's the total source voltage then in this simple series circuit? We've got 6 sources and 1 resistor. You'll notice the polarity first, all the same direction. So it's 6, it's 12, it's 18. We've got 18 volts across a resistor. The polarity of each source then is the same. The sources are connected in the same direction. So 6 volts, 6 volts, 6 volts gives us 18 volts of equivalent voltage. So the voltage increases, the current will be the same in each of these. Remember that. Whenever you're lashing batteries together, if you put the batteries in series, you increase the potential, the voltage, but you do nothing with the current. Okay, so the 3 individual sources then can be replaced by a single equivalent source of 18 volts. So there's your equivalent across a resistor. So many circuits use positive and negative power supplies. A dual power supply then will normally have 2 independent outputs as shown. Okay, so we've got output A, we've got output B, and we've got the associated meters associated with them. Okay, so show how to connect 2 12-volt outputs from a power supply so that there is a positive and a negative output. So if we look at the diagram below, the positive output of one supply is connected to the negative output of another supply. You would do the same thing with batteries. Okay, it's connected from the positive to the negative output of the second supply. The ground terminal then is connected at the same point. So you can see we've got a ground from the output here to the ground there. Okay, and you'll see some of these things in the lab if you have to do a lab where you have to tie a power supply together. So the next thing that is introduced in your text is something called Kirchhoff's voltage law. There is also a current law. Kirchhoff's voltage law is a fundamental circuit law that states that the algebraic sum of all the voltages around a single closed path is 0. Or in other words, the sum of the voltage drops equals the total voltage source. And that's something that you'll be using a lot when you are doing your analysis of circuits throughout your course, throughout your career in engineering technology. So when we come back, we're going to take a look specifically at Kirchhoff's voltage law, and we'll start with this simple series circuit.